over the course of the year to cause the seasons.
So the question comes up that why would Polaris stay in the same place if the Earth is tilting? Polaris is way up in outer space, and the Earth is down here, and like I say, Polaris is a long ways away from Earth.
By the sun physically moving up and down from the celestial equator. It sounds simple, but what are the actual implications of that? Here are the sun and the Earth. At this scale, the Earth is about 1/20th of a pixel across. In our creationist model, the Earth is fixed, and at the March equinox, the sun is here on the celestial equator. The sun circles the Earth with the rest of the universe once a day. Over the next 3 months, the sun spirals around, getting higher in the sky, giving summer in the northern hemisphere. If maintaining roughly the same distance from the Earth, this means that the radius of the circle it describes decreases as it heads towards the solstices by about 12.4 million kilometers. Somehow. As if that didn't defy enough laws of motion, it then spirals down towards the celestial equator again, through the autumnal equinox and on to the winter solstice. This cycle then repeats each year. If you want to say, well, the sun just moves up and down instead, which would be simpler, then you have another problem. It'll end up over 163 million kilometers from the Earth, and with an angular diameter of about 29.27 minutes, instead of its current minimum of around 31.5 minutes. That doesn't happen. But the geocentric picture gets more complex, because the distance to the sun does vary on a cyclic basis. The sun is furthest from the Earth in early July, and closest in early January. Measure its angular diameter if you don't believe it. This makes the motion of the sun even more complex for the geocentrist. The sun isn't furthest or closest at each solstice. If we project those back and use a simple harmonic motion to find monthly intervals from the solstices, we can plot the changing distance of the sun through the course of a year, and it'll look rather like this. Combine that with the daily circling of the Earth, and the crazy sun spiral idea is how geocentrists think the seasons work. Naturally, they have no explanation as to how or why any of this takes place, let alone anything that can explain the complex motions needed for their idea to make the year the orientation of Earth's axis remains virtually constant. At the summer solstice, the north celestial pole is pointing towards Polaris. 3 months later, at the autumnal equinox, it's pointing at Polaris. Come the winter solstice, it's still pointing at Polaris. And at the vernal equinox, it's pointing at Mars. Not really. Polaris. The orientation of Earth's axis, that is, the direction it's pointing to in space, does change, but not on the annual timescale that Fernball thinks it does. The Earth is not a perfect sphere, and the gravitational pull of the Sun and the Moon act on its equatorial bulge. This causes small size, something that puzzled the ancient Greeks. Here's how Mars moves against the background stars from the 11th of October 2011 to the 11th of July 2012 at weekly intervals. We see it slow down, reverse in January 2012, and then resume its easterly motion from mid-April. We can measure the distances to the planets easily, so what does this motion look like over months when seen from above a stationary Earth? From the nice neat circles posits the notion that the planets orbit about a point, which itself circles the Earth. Whilst Ptolemy's voluminous calculations remained of use, they were far too complicated and unsatisfactory to astronomers of the Middle Ages, and we don't use the concept of epicycles today. Let's go on looping tours of the heavens becomes even more questionable when you include the supposed daily rotation of the entire universe. There is more that it cannot explain, and its effect on the other planets needs to be considered. If the sun were really magically moving up and down in space just to make Earth such a lovely place to live, what happens to the sun's axis of rotation? If it changes so that our view of the sun differs little throughout the year, then the tilt of the sun's axis must change. As the sun spirals up to the June solstice, the sun's rotational axis would have to tilt to match. Also, to keep the view of the sun consistent throughout the day, the sun's rotational axis would have to precess once a day as it circles the Earth. The degree of precession must also change every day as the sun travels its crazy spiral. When on the celestial equator, the sun's rotational axis will have no precession. It must then increase again as the sun heads to the December solstice. There is no sensible mechanism by which this can happen, let alone produce the jolly convenient, annually repeatable result that it does. So what else might be going on with the geocentric sun? If the sun's axis of rotation stayed the same throughout the crazy spiral, that would make life easier for the sun. It would also give us that this infantile explanation of the seasons is that crass is the cause of them. If that were the case, then the seasons on all the other planets must also have a one-year cycle, wherever a planet happens to be on its circuit of Earth, because the sun supposedly moves up and down in space once a year. Consider Mars. Its seasons aren't annual. Spring is about 7 months, summer about 6, autumn 5.3, and winter a touch over 4 months. Why? Because the length of the Martian year is 1.88 Earth years. Jupiter's seasonal cycle clocks in at 11.86 years. Saturn, 29.46, Uranus, 84.1, and Neptune, 164.86 years. How can planets go through their 4 seasons in these times if the sun is moving up and down in space once a year? Of course, the primary reason for the observed seasons on the other planets is the same as for Earth. The planets each have their own axial tilt, which results in changing seasons as they complete their orbits of the sun. Geocentrists might like to note the stunning coincidence between the length of each planet's year and the time it takes to orbit the sun. Crass also introduces strange behavior to the planets. Whilst it would be simplest to think that they just circle the Earth on or near the plane of the celestial equator, this isn't what we see. On the solstice of December 21st, 2012, you can go out and see Jupiter. It'll be 21 degrees above the celestial equator. How so? The sun's position against the background stars moves from west to east over the course of the year by a little under 1 degree per day. This traces a line called the ecliptic, which also defines a plane. In reality, this is the plane described by Earth's orbit, and is tilted to the celestial equator by 23.5 degrees due to Earth's tilt. Observations of the planets show that they are always seen near the ecliptic. This is perfectly consistent with heliocentrism, but not with geocentrism unless the planets move from the celestial equator. Because the geocentric Earth is fixed and the sun moves up and down, the plane of the ecliptic must therefore tilt up and down throughout the year with the sun. Extraordinary path through three-dimensional space as the seasons roll by. We saw that the sun had its crazy spiral. All debris trails cross our path, of course, but that most famous comet, Halley, gives us 2 showers each year. The Eta Aquariids in early May, and the Orionids in late October. With geocentrism, Earth is static. Comets orbiting the sun, as they do, will never have orbital paths that cross ours, because geocentrism doesn't give Earth the luxury of a path. Similarly then, any debris that remains along the comet's path also won't meet our atmosphere. Geocentrists are left with 2 mechanisms by which cometary dust can enter Earth's atmosphere. Any comets that pass between Earth and the sun could have the lightest dust particles pushed our way by radiation pressure. This wouldn't work because the particles would drift into the daylight side of Earth, so we wouldn't see them anyway. On distant motes of dust acknowledges that small masses have higher acceleration towards larger masses than the reverse. This leads to the interesting question of why they think this goes around this, when everywhere else in the universe the barycenter of 2 orbiting masses is always closer to the larger mass. And how would a comet like Halley, with a 76-year orbital period, produce 2 meteor showers per year in the geocentric universe anyway? In short, it wouldn't, because geocentrism, whilst spinning like a top around Earth every day with the background stars, and whilst geostationary satellites sit virtually motionless, somehow. 4,114,032,729.619 kilometers. Earth at perihelion is a little under 150 million kilometers from the Sun. If we consider the range of distances that Neptune can be observed to be from the Sun, we find that it is outside the maximum bounds of the geocentric universe. Neptune then must be circling the Earth faster than our nearest star, Proxima Centauri, that's just 4.24 light-years distant, would have to be circling the Earth at 9,750 times the speed of light. The center of the galaxy, around 26,000 light-years away, would have to be circling the Earth at around 60 million times the speed of light. The Andromeda Galaxy, 5.8 billion times the speed of light. How do intellectually lazy geocentrists Geocentrism can explain a geostationary orbit, the special case of geosynchronous orbit where a satellite is situated above the equator and appears motionless. Both have an orbital period of one sidereal day. Geosynchronous orbits, however, need not be circular, whereas geostationary orbits must be. Two orbits with the same semi-major axis will have the same orbital period, so this is what allows for the distinction. We'll use a circular orbit here since we're talking about a geostationary satellite. We saw in part 3 how gravity provides the centripetal force for orbiting bodies, and we can use those same equations to calculate the radius of a geostationary orbit. The mass of the satellite cancels out. As we found in part 3, the mass of the orbiting body is irrelevant to the orbit itself. Multiplying both sides by t squared r squared, we find that r cubed 4 pi squared equals gmt squared. Rearrange and r cubed is gmt squared over 4 pi squared. We know the universal gravitational constant, we know the mass of Earth, and we know the orbital period t in seconds. Plug those in and take the cube root, and we get an orbital radius of 42,166.6 kilometers. The equatorial radius of the Earth is 6,378.1 kilometers. Subtract that and the orbital altitude above the equator comes out as 35,788.5 kilometers. This is very close to the altitude at which geostationary satellites orbit. In practice, Earth's gravitational field isn't uniform, because the distribution of its mass isn't uniform, so there are valleys in the gravitational field which satellites tend towards. A signal to and from the satellite will travel over 71,500 kilometers. Divide the distance by the speed of light, and we get a figure of 0.24 seconds. The orbital distance is why communications via such satellites introduce a quarter-second delay at the equator and longer at higher latitudes. would crash back to Earth unless they were acted on by a constant thrust to counter gravity. A typical communications satellite may have a mass of up to 6 tons, but let's go with 5 tons. The force acting on our 5-ton satellite due to gravity works out as 1,121 newtons. This force needs to be applied constantly to the satellite to keep it in a stable orbit. Satellites have thrusters to allow for orbital adjustments, but not to apply a constant thrust for the entire life of the satellite, which could be up to 15 years. That presents the obvious design challenge of carrying 15 years worth times 1 minus r over h all over the root of 2 mu times h to the 3 over 2. Mu is the universal gravitational constant times the combined mass of the two bodies, Earth and our 5-ton satellite, the latter being insignificant. It's fallen from its orbital radius of 42,166.6 kilometers to the equatorial radius of 6,378.1 kilometers. Plug in the numbers, crunch them out, and we find that after less than 4 hours satellite is moving through space, but because space itself is rotating around Earth, if you match the two speeds, then hey presto, a geostationary satellite. The space excuse is that an object with no motion against the rotation will move with that space. Consider a rocket launched from Earth out into the solar system. The rocket is steered on a perfectly straight course away from Earth so as to have no motion against the rotation of space. An observer on the ground would see the rocket head westward and circle the Earth once a day. This doesn't happen. If rotating space reaches the surface of Earth, the atmosphere as a whole must be constantly moving appropriate to its latitude, like a geostationary satellite. Unless, of course, geocentrists are claiming that their rotating space for some reason stops rotating above the atmosphere, or that their relativity excuse only applies to satellites and not to gases. Sit in your chair and pretend that a rotating coordinate system is whizzing westwards at up to 1,000 miles an hour depending on your latitude. It doesn't change the fact that you don't have to put any special effort into moving east. It doesn't change the fact that gravity is doing a nice job of keeping you in your seat. And so it is that rotating space or not, geostationary satellites is that gravity drops off to zero close to Earth, meaning that you can just put a satellite up in space and leave it there. As you do. Here we have the same problem of a supposed solution given with zero evidence that doesn't work elsewhere. This explanation would allow geostationary satellites to be placed at any altitude beyond the range where gravity mysteriously stops working. We saw the benefits of being able to do this earlier, and we know that it doesn't happen. If gravity has a much shorter range for the Earth, it must do so for all other objects too. This leaves a question as to why periodic comets exist. They go around the Sun, so as soon as one gets out of range of the Sun's gravity, it's the current home of the Herschel and Planck telescopes, and will be home of the Gaia Observatory and the James Webb Space Telescope. The L1 point is the home of SOHO, giving it its uninterrupted view of the Sun. Both the L1, its orbit is inclined at 51.6 degrees to the equator. It suffers orbital decay due to drag of about 2 kilometers altitude per month, so the altitude of its orbit needs regular correction. It's consistent enough from one night to the next that we don't need to worry about it here. On the 25th of January 2013, its orbit had an apogee altitude of 420 kilometers and a perigee of 401 kilometers. Its orbit is very nearly circular. Adding these values to Earth's equatorial diameter and halving gives us a semi-major axis for the orbit of 6,788,600 meters. Deriving from Newton's form of Kepler's third law, the period of an orbit is 2 pi times the square root of the semi-major axis cubed over mu. As before, mu is the standard gravitational parameter, which works out as 3.987 times 10 to the 14. Plug in the numbers and the period of the ISS's orbit works out to be 5,566 seconds, or 92 minutes and 46 seconds. For the geocentrist, observing the ISS should be an easy experience for those along its flight path. Divide the orbital period by the length of the sidereal day, and we find that the ISS completes its orbit in 0.065 days. In this time, the Earth will have rotated 23.26 degrees underneath it. Sadly for geocentrist observers, the reality is that they will have to wait longer than an hour and a half before the ISS tracks the same path across the sky again. The reason for this, of course,